Welcome to the Explainer. Today, we're going to tackle a classic physics problem that looks way more complicated than it actually is. Seriously, by the end of this, you'll see it's all about a few simple, really elegant ideas. So let's just dive right in and break it down.
All right, so what are we actually dealing with here? Picture this. You've got four different forces, all pulling on one single point. Each one has its own strength, its own direction. They're all acting at once. The big question, the whole point of this is, what's the combined effect? When you add it all up, where does that point actually go?
So, our challenge is to find something called the resultant vector. And don't let the name fool you. It's really just a fancy physics term for the one single force that does the exact same job as all the others combined.
You know, if you were to draw this out, it just looks like a total mess, right? A bunch of arrows pointing every which way. And trying to add those diagonal arrows directly? Oh, that would be a huge headache. But guess what? We're not going to do that. We have a much smarter way to handle this.
Here's the secret sauce, the big idea. We're going to stop thinking diagonally altogether. Instead, we're going to simplify everything into just basic horizontal and vertical parts. It's kind of like giving someone directions. You wouldn't say, go 2 miles northeast-ish. No, you'd say, go east for a mile, then north for a mile. In math terms, that's just our good old x and y axes. And the way we do this is by breaking every single one of those messy vectors down into its components. Basically, we can take any diagonal arrow and translate its journey into two simple instructions: how many steps to the side and how many steps up or down. These little horizontal and vertical pieces, they are so much easier to add.
Okay, so this gives us a really simple three-step roadmap. It's our game plan. Step 1, break it down. We'll find those x and y components for every single vector. Step 2, add them up. We'll sum up all the x's, then sum up all the y's. And finally, step 3, find the resultant. We'll use those totals to build our one final vector. This method literally turns chaos into clarity. Let's get started with step 1.
All right, we're going to tackle each of these four vectors one by one. And you know, to keep things from getting messy and to make sure we don't make any silly mistakes, we're just going to use a simple table. That's the best way to keep everything organized.
Okay, let's take a look at this table. For a vector at an angle like our vector A, we just pull out some basic trig, right? Cosine always gives us that horizontal, or x component, and sine gives us the vertical, y component. Now, some of these are even easier. Look at vector B. It's pointing straight along the x-axis, so its y component is just 0, no vertical movement at all. Vector C is pointing straight down, so its x component is 0, and notice that negative sign on the y? That's because it's pointing south. And for D, since it's pointing down and to the left, you guessed it, both its x and y components end up being negative. See? This table just organizes all that messy info perfectly.
And just like that, the hard part is over. Seriously. Now that we have all our vectors neatly broken down into their x and y pieces, step 2 is a piece of cake. It's just simple addition. All we have to do is add up the numbers in each column.
Okay, first up, let's find the total horizontal effect. We're just going to grab all the numbers from that x component column. So we've got a positive 7.5, a positive 10, a 0, and then that minus 44.
And when you punch that in, you get a grand total of negative 26.4. Now, what does that number actually mean? It tells us that after all that pushing and pulling in the horizontal direction, the net result is a force pulling to the left.
All right, next up, you know the drill. We do the exact same thing for the vertical forces. We're just going to sum up all the numbers in that y component column.
So we've got a positive 13, a 0, a negative 25, and a negative 23.5, which all adds up to negative 35.5. And again, this tells us the story. The net vertical effect is a pretty strong pull straight down.
Okay, so this is the crucial point. This is where the magic happens. Our entire problem, which started out as this complicated mess of 4 different diagonal forces, has now been boiled down to just 2 super simple ones, one pulling left and one pulling down.
And this just shows you how powerful this method is, right? We've gone from that crowded, confusing diagram to a simple right-angle triangle problem. That's it. We've got one leg of the triangle going left with a length of 26.4, and the other leg going down with a length of 35.5.
So how do we find the overall strength, or the magnitude, of our final vector? Well, we get to use an old friend, one of the most fundamental tools in all of geometry, the Pythagorean theorem.
We just plug our two totals, r and ry, right into the formula.
Because they form the legs of that right triangle, the hypotenuse, which is the actual length of our final vector, is just a simple calculation away. Square them, add them, take the square root.
And when you run the numbers, you get 44 units. And that's it. That is the combined strength, the single net force of all 4 of those original vectors pulling together.
But wait, we're not quite done yet. Remember, a vector needs 2 things, strength and direction. We've got the strength, 44 units. To get the direction, that final piece of the puzzle, we use another trig function, the inverse tangent. It's a really neat trick for finding the angle when you already know the 2 legs of a right triangle.
And we can do a quick sanity check here, right? Our total x was negative, meaning it pulls left. Our total y was negative, meaning it pulls down. So does it make sense that our final answer is a vector pointing down and to the left? Absolutely. It's got to be in that third, or southwest, quadrant.
So, look, the big takeaway here isn't just the number 44. Who cares about that, really? The important thing is the powerful, reusable method that got us there. Think of this as your new vector-solving toolkit.
Yeah, this should be your new mantra for any vector addition problem, no matter how many vectors they throw at you. Break it down into x and y. Add up the x's, add up the y's. Then rebuild the final answer with Pythagoras and inverse tangent. It's a foolproof system. It works every single time.
And you know, this really makes you think, doesn't it? This whole divide and conquer strategy, it's not just for physics. Not by a long shot. It's a fundamental approach to problem solving that you can use almost anywhere in life. The principle is always the same. Whenever you're faced with a big, messy, complicated problem, just break it down into smaller, simpler pieces that you already know how to solve.